To relax it, we'll be better next time I try. And even if I still can't do it, yeah, you know that I'm gonna stick to it. Yes, it's all about going through it, and I'm gonna tell you why. Whoopsie, whoopsies, I made a mistake and it's okay. It's okay. Whoopsies are what it takes to get better and better every day. Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today. Woo! Whoopsie, 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 whoopsies.
I'm a little embarrassed when I look at my drawing compared to this. I'm just not getting anywhere with this. It makes me wanna hide. Aw, don't be embarrassed. Don't hide.
You should have seen mine the first time I tried. It took a lot of whoopsies to look this way.
No one's perfect on their first day. Whoopsie.
Whoopsies, I made a mistake and it's okay.
It's okay. Whoopsies are what it takes to get better and better every day. Whoopsie, 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 whoopsies.
Well, what about this? I want to jump rope, but nope, I just can't do it.
Well, not yet. Come on and practice with me. You'll see there's nothing to it.
Whoa! Whoopsie.
Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today. Woo!
It was only a dream, the waves of evil crashing over us. It was only a weak and faithful scream beneath the battlements. I know it's hard to follow before it's too late. Wake up, my love, please don't give up on me. It's hard. Wake up. It was only a dream, the waves of evil crashing over us. It was only a weak and faithful scream beneath the battlements. But I know it's hard to follow before it's too dark. Wake up, my love, please don't give up on me.
What is up? What is up, you guys? We are back at it again. Another day at the grind. Another amazing day. We are officially 1/3 of the way through. 1/3. You guys should feel great about yourself, right? We are chugging through this. You are almost done, right? The finish line is in sight. Still kind of out there, but it's in sight now, alright? Let's see. If you're returning, well, hello. It's nice to see you again, alright? It's nice to see you again. If you're new, well, hello. It's nice to see you join us. If you didn't know, we're Rookit, nonprofit based here in the US of A. We like giving away a lot of free things, including this class, alright? But additionally, if you go to our site on our blog, we have our week 5 giveaway. Go over there, fill it out, completely free, and you could win yourself one of our amazing sweaters. Now, if you like what we're doing and you want to help support us financially, let me go and change the music over here. If you want to help support us financially, you can donate to us, and depending on how much you donate, you'll get different types of rewards, like our epic stickers, our awesome shirt, look at this thing, so epic, and of course our sweater. All right, epic sweater. All right, if you want to follow along, go ahead and go to our GitHub. We have everything listed there that you need in order to get our cert. It's going to be the CompSci cert roadmap. If we go down here to operating systems, awesome. We are chugging along here, almost done. And today we're going to be talking about some OS processes and designs. All right, so we shall get into this. So a lot of this is going to be pretty much an overview look. We don't really need to get too much in the weeds, but an overview look on how everything goes, how data is processed from the lowest level up and from up all the way down, and just the general structure / architecture of everything, because it's important to know, especially when you go out developing, because these things will be very relevant. Let me pull up my stuff here. I was in the middle of doing like a million things, and then I was like, oh, look at that, it's time for us to start. I need to stop real quick. I had to stop a bunch of stuff I was doing like mid-processing through it, and it was already like 10 minutes in, and I had like 10 minutes left, but I had to stop it in the middle. I was like, oh man, I gotta redo all of this again now. It's alright, it's alright. Let us see here. Alright, sweet. So let's go ahead and jump into this. So in every operating system, there's this concept of rings, all right? You seen Lord of the Rings? It's kind of the same, all right? Kind of the same, all right? Lord of the Rings, that's what we get in our operating systems. All right, let's see. OS rings. Powers of good. Oh boy, here we go. Rings of protection, all right? This is straight out of any type of lore book you've ever read, all right? Same thing, rings of protection. So these rings are purely conceptual, all right? They're purely conceptual. Everyone and their dog has a different way of listing them, has different types of rings. They have more than 3 rings, less. I guess this person has negative rings. Look, there's no set standard for this, all right? It's all very arbitrary. It's more of the concept that's important, and so we're going to talk about it a little bit. So you got the Wikipedia picture. That one seems really small. There we go. All right. So in your OS is responsible for pretty much everything, all right? It's responsible for all the maintaining all the applications that you're doing, the users that are on the platform, permissions, and hardware interactions, all right? It's doing a lot of work for you that people take for granted every single day, and that's great. When things work, they just work, you have no issues. When they don't work, things are glitchy, they crash, and people notice, and it gets irritating, all right? No one likes something that is irritating. So in regards to how things function. We have this concept called the rings, right? The rings of doom, or sorry, not doom. The rings of privilege, rings of privacy, protection rings. Now, what this does is it kind of conceptualizes really basically, sorry, it conceptualizes very visually to you on who is allowed to do what and how much can they get away with. Now, this differentiates based off your operating system. Like Windows, this kind of holds more true, but on Unix, more or less, because if you are the root user or you're running those sudo commands, you can pretty much get into ring 0. But the idea is ring 0 is going to be for your kernel or any like processes that are core to your operating system. All right, it's going to be it's going to have absolute god privs. All right, absolute god privs, and not even that, further than the god privs, because it can now dictate reality. It can change how memory space is laid out, oriented, etc., etc. When you get rootkitted or bootkitted on your device, it will modify and have root or ring 0 privs. There is no concept of privileges really in ring 0. It is just you get to do whatever you want and shape things however you want. So it's really important that no one gets to ring 0. So your operating system by default will try to keep you away from ring 0 as much as possible, because there is no holding you back. If something gets messed up in there, it could destroy the whole computer, or it could be potentially harmful. So ring 0 is the highest perm mode, all right? And you only want really your kernel and any other important operating system stuff to be in there. Now, typically, people will fill out ring 1, 2, however they would like, but no matter what, the common conception amongst everyone that's using this ring topology is that at ring 3 is where the user lives, all right? That's where you will be, your normal account when you're running applications or programs. That's where your stuff will be, all right? So there's a couple of levels away from the core user or ring 0 you are, and this is to keep you protected, to keep you abstracted, to allow you to do things more easily without having to worry about things breaking or having to do a bunch of weird memory management stuff, etc., etc. So let's see here. So in regards to kind of how this works conceptually, we have there's actually some interesting things that happen in your operating system. So let's go ahead and bring up Paint. Oh, we've been painting a lot recently, and I know you guys have been loving it, all right? So what this interaction kind of looks like is, I'm gonna go ahead and freehand these, all right? Because we're going risky out here. So here's ring 0. Oh, that's a perfect circle. So this is where your kernel is going to live. And then conceptually, there may be some other rings. And then let's say here's you. So this is ring 0. Let's just say this is ring 3. And this is you, the user. Now, since operating systems are set up this way, you can't yourself actually make a file or reserve memory or actually do anything yourself. Even though it seems like you're doing it, you're not actually doing it. Every time you try to print something out on a CLI, load up a web page, pretty much anything on your computer, what's actually happening under the hood is your user account is making a request to the kernel account. Let me do this in green, or I guess in blue. You're actually making a request to the kernel account and being like, hey, baby, I love you. Please let me do this thing, all right? Look, my creds say I'm good for my money, all right? Just take me back. And then your kernel will evaluate what you've requested, and based off of that, they will either allow it to happen and on your part, they will execute that logic for you. Or they'll just straight up deny you and say, no, you're not going to be able to do that. But you're interacting with the kernel, all right? You don't actually do anything yourself. You ask the kernel to do it, and then the kernel will execute on it. So when you want to write to disk, the kernel will actually write to disk for you. Everything goes through the kernel, all right? Any questions on that? And why is it like this? Because the kernel, again, is a part of the operating system, and its job is to manage how things go onto disks. We talked about disks yesterday and how they're stored all weird and so forth. Its job is to do all that for you. Same thing for memory. So your RAM, I know I have RAM sticks right here. Here we go. More visual aids. Here we go. We got our RAM sticks, all right? On RAM. All right, this is also storage. This is your memory. This is all managed by your operating system. Your operating system will manage where stuff goes into RAM. By default, for you, you don't do that. You don't manage it. Sure, you may seem like you do at times, but you never do. Your OS will always be in control unless you bypass that, which hopefully you know what you're doing. If you bypass it, sorry, I got distracted there for a second. So how this interaction usually goes is the user over here is running, let's see. The user over here is running some type of application or running some type of program. What color we want to use? There we go. You're running some type of program, all right? And your program will want to do something, all right? So when you want to do something under the hood, you're actually making a request to the operating system. Typically, it's going to be called a system call handler, all right? This is your handler, all right? They're going to handle all your goods for you. It's pretty much a middleman, right? It's a middleman that's going to handle all the calls that you make to it, because in programming, you call functions. That's how you go about programming, all right? It's called calling them. So this is going to be the handler for your calls, and then based off what you're trying to do, it will then, on your behalf, talk to the underlying kernel services. Okay, I'm just going to do okay. We'll talk to the underlying kernel services, which then will reach back out to you with whatever you try to do. Now, this is where these other rings come into place, because if you have, let's say, an Wi-Fi card, an Ethernet card, a graphics card installed on your board, those are going to have their own drivers. So your operating system will only be in control of a certain amount of stuff. Any additional hardware that you have that's not really covered by the operating system completely, you'll have to install drivers, and drivers are going to be kind of your middleman in regards to when you want to communicate with them. The kernel will still occasionally be in there to help facilitate what's going on, but you'll end up talking to the drivers, which will be pretty much the ring zero of that association. It's not technically in ring zero, but I think you guys kind of understand what I mean. Makes sense? Any questions on that? So you can see what these are called if you look them up. We kind of saw them in the man pages. So let's go man pages. Might not have been apparent at first. Here we go. So if you look right here, we got a couple different man pages for different things here. One of them is called system calls, all right? This is not by coincidence. This is going to be what you call. This is going to be going to the system call handler, all right? So system calls are functions that are built into the operating system at the kernel level, and when you call this, you are actually directly talking to the kernel. And there is a system call here for everything you do when you're programming. whether it's Python, JavaScript, Java, Java, C, C++, etc., etc. It will always go through one of these system calls. As you can see, there is a lot of these system calls. All right. So just so you know, you can make all your programs just by calling these system calls if you want. Don't, that would be atrocious, but you can. All right. Library functions will be functions that are built on top of those. All right. And some of them may include driver functions, but I think that for the most part will be handled by this section, I believe. Don't get me wrong, or don't quote me on that. All right. Any questions? I don't really see any questions, so we're gonna just keep trekking along here. All right. So each one of these operating systems are going to implement this ring concept in slightly different ways. They may add a bunch of middlemen. They may have very few middlemen. You may not actually get all the way down to the bottom sometimes. It just always depends. But you're always going to be going through an API, which stands for Application Programming Interface. Correct. You guys got it again, all right? Told you we'd be hitting that a lot. And that's what's happening when you're, there we go, when you're using these. This is going to be your API to integrate with the kernel, all right? Because you're interfacing with the underlying items here. So if we, let's see if we can get a pretty picture here. If we do the Linux, oh, that one works. Perfect. This one's nice too. So you can see kind of the concept here. This one kind of works also. But you can kind of see that concept of the rings in play right here. So what will happen, and this is dependent on your program, and it's not always like this. Sometimes you may go straight to the kernel and won't have to talk to the shell middleman, but typically your application will interact with the shell or some type of library here at this layer below, and that library or shell on your behalf will then integrate with system calls, which are not technically on here right now, but the system calls, which I just showed you in the man pages, which I think we no longer have up. It will talk to the system calls on the man pages, which then will automatically negotiate with the kernel below. All right, and the system calls responsibility is going to be the permissions. All right, they're going to handle the permissions at that level, and that's when it will be resolved. And anything that's past there is going to be in kernel god tier mode, and it will just run. All right, it will just run and execute. So it's important to stop anything before it gets to that mode. All right, and yep, the kernel will talk directly to the underlying hardware. Now it is important to know that you can't just swap your hardware. Hopefully this was covered with Taylor, but the commands your kernel uses are kind of determined when you first install your operating system on your computer. If you have an Intel computer, CPU-based computer, you're good. As long as you keep upgrading your computer to new Intel CPUs. If you want to go to AMD or vice versa, from AMD to Intel, you're going to have to reinstall your operating system because, again, it's the Wild West in programming world, and they make each other's hardware are uncompatible with each other to a certain extent. All right, to a certain extent, they're uncompatible with each other, so you would have to reinstall the operating system all over. Alrighty, let's see if we can do the same thing here for Windows. Windows OS layers, and get a pretty circle picture. Will this one work? Kind of. It's missing what I'm looking for here. think we're gonna have to go with the picture like this. God, that one's terrible. Windows is going to be a little more complicated, as you can tell. All right, so let's go and open this one in a new tab. Windows is more complicated because Windows is a beefier, heavier, crazier operating system that is typically capable of doing a lot more complex things than Linux computers can. All right, so you're gonna have your user mode, which is up here. So if we think of the rings, it will be user mode, and then another ring will be this executive, then another ring will be this kernel mode, another ring will then be HAL, and then you'll have hardware. All right, so there's a couple of rings here. You can kind of just think of them as each one of those layers that go from one side to the other. All right, so this is where your applications will be in user mode. And same thing, there's an API you can mess with. It's called the Win32 API, I believe. Is this it? I can't remember directly. But there's an API. I think this is the wrong one. Is it this one? Is it this one? Regardless, you can look up the underlying API for Windows, which is the same thing that we showed off a second ago for Linux. All right, your application will directly communicate with these underlying API calls to the operating system. All right, the operating system will then take it from there and interpret your commands and then try to execute on them. All right, there's a bunch of services in here that it will utilize in regards to whatever you're trying to do, but it will, be checking your permissions first and foremost here before moving forward. After that, then it will go to the kernel for any additional execution that may be done, and it may not just end there and go straight up, or it may go down further. There is a layer below the kernel in Windows, and that's called the HAL. All right, the HAL is the hardware abstraction layer, and that is meant for interacting, all right, with the hardware devices. It's a layer completely isolated from the kernel for interacting with hardware. It's supposed to help with stability and security. All right, it was put there very much intentionally quite a while ago. Let's see here. And then for Android and iOS devices, they're both going to work pretty similar to the Linux model that we showed. All right, so if we go back to our Linux ring layer, where you're going to have an application, and typically it will be sandboxed, so you'll have to talk to the underlying sandbox framework or layer, basically, to get permission to communicate outside of the sandbox. Then your request will go outside of the sandbox in order to then communicate with whatever it needs to communicate with, and then the response will go back up. All right, so why is this being brought up? Because this brings in potentially multiple points of failure. You can have failures on different levels of these structures. So it's important to keep this in mind and know about it, because when error messages come up, you're able to read them more intelligently and be able to solve where the issue is. Maybe figure out it was a permissions issue, or figure out that maybe it was a driver issue, or figure out that you're making the call wrong, or the permission was filled out wrong, or I don't know, figure out exactly what went wrong. So in regards to iOS, which is going to be slightly different, iOS is going to have, let's see if we can bring up OS layers. So iOS is the only one that's going to be a little bit different because that's made by Apple. It's not as tightly coupled to, the Linux. So back in the early days of iOS, there was the Cocoa library. It was pretty big, pretty massive, and that's what you used in order to make all of your pretty pictures and get more powerful functionalities for animation. Now things are pretty extracted away. You don't really that often communicate with the Cocoa library anymore, but it still exists and it's there. So when you build an application on iOS, that's going to be kind of the middleman. That's going to be kind of your underlying API for the operating system that you'll be communicating with, which will then funnel down, like I said before, to the other layers, and it will start that communication of, can I do this? Am I allowed to do this? If you are allowed to do it, it will then allocate and move the process along as needed. All right. So iOS has these extra layers, particularly the big keyword there is Cocoa. All right. Cocoa will be managing a lot of your niceties over in iOS world. Let's see. Any questions on that? What's up, Kamal? And that's pretty much it. The big thing for these points are going to be just these pictures that we saw in the layers of how communication gets down to the kernel level and back up. The layers are what's most important, and just knowing in general what these layers are. For Windows, know the HAL is a thing below the kernel, and it's there to interface between the hardware and the kernel. All right, separate layer. It's different. It's unique. Very important. All right, for Linux, the simplest one. It's pretty much as close to the ring picture as possible. Very simple. Android is pretty much the same. The only the only thing is you may be escaping the runtime. All right, and then the last thing would be iOS, which again, key term is going to be Cocoa, because you're going to be integrating with Cocoa, and that will be messing with, let's see what this one says. Yeah, you'll be integrating with that one in order to do a lot of your underlying processes on the way down. There's a lot of good infographics here that you can use and analyze. Yeah, these are pretty good. So you can check these out. I highly recommend them. And they will, especially if you want to get into mobile development, this will help lay out and have you understand where everything is and how it works a little bit better. This is for Linux. I was about to say this doesn't look the same. There we go. So you got Cocoa here at the top, which is doing all your fun stuff. And then right below that is for your media. So this is for rendering your 2D, 3D graphics. So if you ever wondered where any of this stuff lived and what it went through, you can kind of see here conceptually. And again, these would be your quote unquote like rings of privilege or protection, however you want to call it. Any questions on that? That's pretty much all I got for that. I guess that was a little quicker than I thought. Let me see here. What's in the COA? Let me look at these questions in here. Where is my pool? Here we go. Why are you making this difficult for me? There we go. And just looking at some of the example questions. So, an example question. What ring does an application run on? Correct, 3. That's right. How about the kernel? All right. What layer might be specific to iOS? Cocoa beans? Yeah, that's right. There you go. All right. You guys are going to be good. All right. Alrighty. Let's move on, I guess, to the process internals. So, process internals slash interrupts. I don't know why these are kind of separate. My notes just go straight up into interrupts. Did I miss something? No, here we go. I skipped it, that's why. Silly me. Alright, so we've kind of talked about some of these things already. And so as you see moving forward, you're already going to know like 50 to 80% of this material already, because we've already talked about it. We're building upon it slowly. Alright, so when you're trying to execute something, you're going to have a executable. We're going to have an executable, all right? And when that executable executes, as we've seen before, when we load up the terminal, let me go ahead and bring up Ubuntu here. When we load up the terminal here, and we do something like bring in our elf to the party, so pstack elf, we're going to get an output of all of those executables potentially that we ran. There might be some more information there. Alright, we're going to have this indented stuff. But there's also the PIDs, and the PIDs are there for both Windows and Ubuntu. Alright, that's going to be your process ID. So we already talked about executables. Alright, that's something that can be executed and ran on your operating system. A process will also have a process ID. Alright, a process will also have memory that's allocated for it, and you can also view in here the amount of memory it is taking. Every process requires memory to run. Alright, there's no way it can run without memory. Now, a process could have threads. It will have at least one main thread, but it could have multiple threads. And we'll talk about threads here in a second. And let's see. And it will have an identifier, an account identifier that's linked to it. That's going to be whoever executed that program. All right. So those are like the main things, and you can always figure this out by just looking at a process list, whether it's on Unix or Unix-like operating systems or Windows. You'll always see, what ran. This command ran. This command ran. You'll be able to see what the PID is, potentially if it has a parent that is actually remarkable or not. This one is not a remarkable parent, just linking it to my current session, how much memory it's taking, who is the account identifier, who ran it, who's currently in charge of that process, and then threads. All right, threads are handled more elegantly in Windows, specifically if you look at the task manager. So if we bring in the task manager here and we open up this this thing right here, the little arrow, you'll see all of the underlying threads for that program. All right, you can kind of see the same thing on here, but you have to basically relate these parent IDs to your command. You'll see multiple programs with the same parent ID. That's how you know they're all threads underneath a running program. So threads, if we haven't talked to them about them before, threads are going to be different. Let's see. Let's talk about them like actually for fabric. If you have a piece of cloth, it would have most definitely hundreds of threads attached to it. All right. Now, that's kind of like a program. All right. A program can be composed of a single thread, or it can have multiple threads that are woven throughout to make up the program, the fabric of the program. It can go from 1 to infinity. All right. So that's what a thread is. It's usually a bunch of different supporting running programs underneath one parent program that's trying to do something. And this is where you get orphan children from. We've already talked about in computer world, we hate orphans and we kill them. All right, we kill orphans in the computer world. And what an orphan is if I try to end this Streamlabs program, which I'm not, because then the stream would end. If for some reason one of these programs in here, one of these threads did not stop running, but everything else did, it's now an orphaned process. All right, it's an orphaned process, It's running, using up your resources, being a bum, all right? It's taking away from your computer, and it's just kind of there. It's also referred to sometimes as a zombie process, and funny enough, they'll actually be marked with a Z, I believe right here, in what do you call it? In Linux, but those are what you want to try to kill and not have in your program. So if you are spinning up multiple threads, you're multiprocessing or multi-threading your program, you're going to want to pay attention to that and make sure you're killing them all, or else you might have issues in the future. Alrighty, let's go ahead and move on here. So we just talked about threads a bunch. Did I miss anything here? Consider. So the reason why you want threads is a process. So when you start a program itself is going to be big. It's going to be hefty. It's going to have a lot of overhead. It's going to be a complete thing, a complete person. All right. It's going to be a complete person. All right. It's going to have everything it needs in order to execute. Threads, though, on the other hand, are very, very lightweight. They have pretty much nothing in them, and they rely on the parent process to give it anything that it needs. All right, that's called, and when you have multiple of those threads relying on the parent process, that's a multi-threaded program. There is multi-process programs where you spin up entire different processes with all of the needed information inside of them. That is a more expensive operation to do, which ideally you want to avoid if possible, because it is very expensive computing wise, because you need a lot more for it. So threads are usually ideal. Your operating system will perform all of the needed logic for executing data in your threads for you automatically. You do need to be smart though, because when you are using multi-threading or multi-processing, you have child processes. So if we look here at Streamlabs, each one of these are pretty much kind of running as their own independent program to a certain extent. But that's where you can run into issues. Because let's say you're the parent process, all right? You're a parent and you have a bunch of threads, let's say your children, all right? And you tell them to go do some tasks because you're annoyed at shit at them, and you're like, get the hell out of here, go, I don't know, pick up 20 rocks or something, and don't come back till you do it, all right? Doesn't matter whether the task was useless or useful, you tell them to go do something. And now your goal is to walk to a bench and sit down so you can relax, all right? If one of them, because again, your OS is handling how they go about doing their tasks. If for some reason, and you have to share this, you know, let's say your operating system has only one CPU, all right? All of this needs to happen seemingly at the same time, but on one CPU. And one CPU, again, can only process 64 bytes per cycle. So multi-processed processes aren't actually multi-processed. They're running one at a time after each other. The CPU is handling who gets to run at any given second. This is where we have issues coming in, because if you're walking forward to that bench, you're like, oh my god, that bench looks so good, I just want to sit down and relax on it. Your CPU may pause you walking to let one of your child processes run maybe all the way to completion before you're able to take another step, which means that your kid is going to come to you and be like, hey, I finished my task, here you go, but you're not ready for it yet, all right? You're not ready for it. It's gave you the data before, and so now things are all messed up, you're angry, you're mad, and your day's ruined. All right, this happens all the time in programming, especially when you do multi-threaded, multi-processed programs. And let's see here. This is where we run into things called race and deadlock conditions, which we'll talk about here in like 2 seconds because I think there was a couple things I missed. Let's see here. All right, so we have a process control block structure we need to talk about. So let's go ahead and Google this real quick before we move on, and then continue with our story and how to potentially fix these issues. All right. So our process control block here, let's see, is a way to keep track. So a way for your operating system to keep track of each process in its current state that it's in. All right, different OSs will have different amounts of information that they will handle, but they will all at least have some of the following that we're going to go over here. They're going to talk about the application name that it belongs to. Let's see, is there a Wikipedia article we can go to? Wikipedia, don't do me dirty. We'll go to Geeks for Geeks because I like their site. So let's see here. Perfect. I like this. So you'll have some type of pointer that will be pointing back, typically, to the original process. Usually it will be either an actual pointer to where it is, or it will be the process ID. What is going on here? I don't want to log in. Process ID, and that will be pointing off to the process name, which could also be in the process control block. You'll also have the state that it's currently in. All right, and there's a couple of states that a process can be in, and depending on the OS or what program you're operating in. So I don't know, let's go to Python multi-threading. So multi-threading in Python, I want the docs. So there's a couple of states that it can be in, and it's usually documented pretty well in the programming language that you're utilizing. So one of the states could be in a lock state. I believe there's a running state, and a wait state. I'm trying to think of the other states. I know they have it listed nicely somewhere. Are these it? I don't know, but there are several different states it can be in. All right, it will also have its own process number associated with it, aka that PID that we talked about. So each underlying thread will have its own PID, which again, we already talked about that. That's what these underlying things are going to be. Let's see, there's going to be a program counter on it, which is going to potentially store the counter, which contains the address for the next instruction that is supposed to be executed for this process. Register, these are CPU registers, which include the accumulator, base register, and general purpose registers. Don't worry too much about this. It's just, you just need to know some of the layout for all of this. Limitations that you may want to be putting on it. Information for files that it may be opening or linked to. So this would also go into potential like IO status information, and privileges would be kind of the last one that you could potentially have in here. Again, we're getting into more of arbitrary land, but this is like some of the information that will be attached to your processes and the threads underneath them. Let's see. Oh, there was a, how did I miss this? But yeah, you can read this up yourself, and it's pretty much the same thing we just went over, right? And it's all pretty much arbitrary on what could potentially be included underneath. It just depends on OS by OS. But the main thing is, you know, these are a thing that exists when, and it gets kicked off when you run a process. We talked about some of the process states, all right? So to go over this right here, Wikipedia is saying that there's going to be, I saw 4 right here, new, ready, running, waited, or terminated. All right, these are going to be five. All right, so there will be some type of mix of these on your operating system. There may be more, there may be less, but you will usually have these, and you can dictate that in your application when you are doing multi-threaded processes through whatever function calls they have here. And this is a way for you to track the process of each one of your threads. You can actually, there's actually functions in here to get the current status of your thread. I didn't really come prepared with the information off the top of my head. I'm kind of forgetting right now. Where is it? Get name. I'm pretty sure it's called like get status. Status. Of course, you have nothing that comes up. I always get done dirty unless I prep this stuff. But there is ways where you can actually pull the current status. I guess one thing would be is alive. So if a thread is alive or not. So this is a way to get some of the statuses. And this could be important. You need to know this is a thing. You can pull a lot of this information out of your children threads if you want to kind of check up on them, monitor them. Maybe you don't want to do certain actions or things until they are done running, maybe until they hit a waiting or pause state. You know, this is totally up to you as a developer, all right? But these are things that you need to know so you can go about programming your logic however you want. All right, let's see here. And we should be good onto concurrency. Let's see. I like this, so we'll run through this real quick. So for example, in regards to the states again, your program will be in a new state for a very, very short amount of time. This would be the equivalent of you double clicking a application and starting it up immediately. All right. It will be at first in a new state until it hits into the next state, which is going to be ready. And ready is going to be that it's in like a queue to be ran. So new is going to be kind of before you get that block of information, knowing, you know, the process block that we just talked about, the process control block. Ready is going to be you are now ready for, and you're waiting for execution. Running means that you are currently running that program. All right. Waiting could be you're held up because you are trying to read information off of the file system. Maybe you're trying to read a big photo or something. You'll be sitting there waiting for it to finish before you can keep moving. And then terminated is going to be when you end. All right. Any questions on that? I feel like we covered it pretty well. Well, let me make sure YouTube's on live chat. All right, let's go ahead and move on and revisit our concurrency stuff here. So our race condition and deadlock condition. So we kind of talked about the race condition. All right. This is very important for programming, for banking, for a lot of different reasons, and you will run into these. All right. There's no way to avoid them. You will hit them eventually when you start making your applications. It's just something that happens, and then you're like, dang, I messed up. I gotta fix some stuff here. So the race condition is, think of it like a race, right? People are running. They're running as fast as they can to complete something. For example, you're heading towards a bench to go relax while your children are out doing something else. All right, it's a race for you to get to that bench and sit down and sleep. All right, to sleep for the love of God before they come back. But what do you know? They came back sooner than you expected them to. That's a race condition. This can be very bad for you. This is when you're getting results or anything in a untimely manner. All right, so it's either quicker than you expected or it takes longer than you expected, but typically quicker than you expected, and you can't really do much more because now you're all like pissed off, cranky, etc. Let's see here. Let's see what exactly Google says. Condition. Wikipedia here. Race condition or race hazard. I've never heard of the term race hazard, but again, we're in the depths of programming world where everyone calls everything 10 different fucking words, all right? So you guys will see that moving forward, if it hasn't already become abundantly clear already. Is a condition in electronic software or other systems where system's substantive behavior is dependent on the sequence or timing of other uncontrollable events. It becomes a bug when one or more of the possible behaviors is undesirable. All right, undesirable is the key word there. So again, I'm trying to think of a good example of a race condition. I think it would be like banking, for example. Banking would be a good one. It would be really awesome for you or really inconvenient for you if this happened, all right? Let's say you're at an ATM, all right? And you're about to deposit some money. But at the exact same time, you have another card that you gave to your brother, parent, whoever, and they're going to the ATM at the exact same time as you. You both are at these ATMs, you put the card in, and you say that you're putting money in, and your parent or whoever, whatever they're doing, they're pulling money out. All right? Yeah, they're pulling money out. No, you're both pulling money out. Let's just go with the example. You are both pulling money out at the exact same time. All right? You're both pulling money out of your account at the exact same time. When you do it at the exact same time, it would be really inconvenient for the bank, but really great for you if both of you guys got there like within a millisecond of each other. You both saw your account information was at, I don't know, $100. All right, is that too much for you guys' bank account? $10? Does that sound better? $10, all right? And you wanted to pull out $1. When you pull out $1, it would be really inconvenient if the bank only registered it as $1 being taken out because you're both hitting at the same time, or maybe that, yeah, just your bank being like getting messed up. I feel like this example is not good. Hold on, there is a bank example I'm trying to remember off the top of my head right now. Let's see here, race condition example. There's a better one that what is it with Google and all these? I mean, that's why we're here, because everyone sucks when it comes to this stuff. But here we go. Is this the bank example? All right. Oh, there we go. So like depositing a check. So you deposit a check at the exact same time. Is this check B for $1,500? Let's read. Example: suppose a map application proceeds to 2 processes at a time. Each process demands the same location data. When this type of racing exists, one of these 2 processes will capture the early value so that the other process can't access it. This is the correct way of going about it. Yeah, let's go with depositing. All right, so you are depositing a check, your buddy's depositing a check, you have $1,000 in your bank account, both of you are depositing a $50 check. If you were to deposit at the exact same time and the logic was bad, you would both see that you had an initial value of 1,000, and then the bank took the deposit and put it to 50. But you lost $50 because since you guys did it at the same time and the bank's logic was bad, there was a race condition, and so it only went up by $50. Basically, the way to solve this is going to be locking. So whoever requests something first immediately locks anyone else out, and they're not able to touch or interact with that thing, whatever it is, until you are completely done interacting with it. And then you can release your lock and someone else can interact with it. Because it would be very inconvenient if you tried to deposit $100, but it only ended up being $50 because there was a glitch in the system. So that's kind of the race condition. Sorry, that was kind of rough to go through for the example. Are there any questions on that? The deadlock condition is literally, if you have any questions, just drop them in. The deadlock condition is file is new, file is currently running, file is waiting for instructions, and file is terminated, basically. File is new, file is new, file is running, currently file is waiting for instructions, file is terminated. Yes, that's basically it for the different processes. Yep, exactly. Sorry, it took me a second to read it through and figure out what it was going on. Deadlock is exactly what you think it is. Two things happen at once and they stop each other from going forward anymore. All right, things become locked. This is where, for example, your program will become not responsive and then you'll have to force quit it, you know. That's because a deadlock condition usually happens, where things are both happening at the same time and everyone freezes because no one knows what to do. Everyone's freaking out and nothing gets actually done. All right, just like the term deadlock, that's what it literally does. Race conditions and deadlocks are very common things that will happen when you're doing a multi-threaded application. They're also very easy to avoid. They are very easy to avoid. All right, there are lots of pre-built things in your operating system to help you avoid them. All right, so you need to make sure you're utilizing them properly. For example of a deadlock condition would be if, say, you were going about something more proper. You know, you were being a good programmer and you were going about you know, putting locks on things so you wouldn't have any race conditions. Well, now you have like 3 processes that want to read the same file, but the first process locked that file up so no one can read it anymore. Those 3 processes are all in deadlock. They can't move or do anything at all. They can't progress. They're just completely stuck until that first file does something. So I guess I should walk it back for a second. Race condition could potentially happen at any time due to not the best programming. Deadlock can also happen even if you are trying to do good programming, because you'll accidentally lock things out. And depending on your logic, you could be permanently locked out. That's where you would need to forcefully close a program. Any questions on that? Let's see if there's deadlock example. I like this picture. Yeah, this is a good picture right here. So process 1 is waiting for resource 2, which is currently being used by process 2. All right, because you want to avoid race conditions. You're a good programmer. But you accidentally introduced deadlock because your resource 2 program, your process 1 program was utilizing resource 1 and put a lock on it, like a good program should. But you're now waiting for resource 2 down here. But you have another thread called thread 2, process 2, which needs resource 1 and currently has a lock on resource 2. So everyone's just locked up and standing there looking at each other like, I don't know, like the movies with everyone with the guns out, and they're like Who's gonna fuck up first? All right. That's a deadlock. All right. Any questions on that? How you guys feeling? You guys want to go over anything else? Because we talked about a good amount of stuff today. We can go over interrupts if you guys would like, or we can just call that a day. Because this goes nicely with this stuff. Up to you guys. So only way out of a deadlock is to force quit. Yep, deadlocks. So there's like, yeah, the only way out of deadlock is something needs to die. Yeah, you have to kill something. If it's a really bad deadlock, the whole program will need to die. If you have self-solving deadlock logic in it, what will happen is either each process may have like a allotted amount of time it's allowed to live, and so it will automatically kill itself after a certain amount of time if a deadlock usually occurs, and that will usually free up whatever is causing a deadlock elsewhere, or just various other types of logic like that. The only way to really resolve it is by killing something. Something needs to die, whether that's the process itself, the process connecting to other things. So if you were to kill its access to resource 1, that would be a way to do it. Ideally, to avoid this, you should really spend the most minimal time ever when talking to other resources. Resources like resource 1 or 2 here would be things like files on your hard drive, would be stuff like networking, would be stuff like, I don't know, holding up certain graphics processes. I don't know. It's usually files. That's what it comes down to most of the time is files, and I guess also memory, because pretty much files and memory, they're both laid out the same way. They both kind of are interacted with the same way, and those are the most commonly or frequently used in accessed items. So that's what's most commonly locked up. Decision says call it a day. All right, I'm down with that. Kwai says I'm down for anything. We'll call it a day. We went over 2 topics today, so we went slightly further ahead than normal. So we'll call it a day then. For tomorrow, look at that, we're almost done here. Tomorrow we'll definitely cover all of 11. I think that's gonna be pretty short, so we might also talk a little bit more about device drivers. And then we got VMs, and then we're on to programming. You can't just eliminate one of the processes to free up the deadlock. Yes, you can eliminate, if you, again, no process, processes usually will never start at the exact same time. Even though you program it to start at the exact same time, they're never going to actually start at the exact same time, because again, your CPU can only process really one thing at a time. It just does it really fast, so it seems like there's multiple things. Even if you have a multi-core CPU, the likelihood of things happening at the exact same time is uncommon. I won't even say rare, because it can happen, but it's uncommon. Usually there will always be at least a couple milliseconds difference. So if the first process was started 0.1 milliseconds before the second process, if it dies, that one process dies 0.1 milliseconds earlier than process 2 will expire, it will free up these resources, and maybe in that 0.1 milliseconds, that's enough time for process 2 to finish whatever it's doing. And then process 1 can be revitalized and finish up whatever it was trying to do. So it's all about order of operations. You'll see this more towards the end of our programming stuff, because this is going to be one of the last topics we do programming wise, because again, it can become messy very fast and make you very mad and make you want to break a lot of things. All right, it's at first not an easy thing for people to grasp. All right, sweet. Any other questions we got? All right, sweet. I don't see any other questions. So that's all I got for you guys today. So tomorrow again, we'll go over interrupts, exceptions, and trap handling. And then depending on how quickly we do that, we'll just move on to device drivers. All right. And all right, sweet. I will see you guys on the next one.